Okay, so what did we do last time again? Abdon. Oh, you weren't here. Oh, sorry. Patrick.
We did predator prey, what files on Terra, and then we switched it to logistics for that.
Okay, that's right. So this was a model of populations, right? Different populations interacting with each other. One of them was preying on the other. It was a wolf preying on rabbits. Okay, so now we want to move over to populations and epidemics. So let's think about not a wolf, but a virus. Okay, and the question is, how should we change our models so that we can model viruses instead of wolves? Okay, so what do you think are differences between viruses and wolves from a modeling point of view?
Viruses grow faster.
Sorry?
Viruses grow faster.
Grow faster, okay, that they can grow much faster, that's right. Yes?
I don't think viruses would compete with each other.
Viruses would not compete with each other.
Like wolves do, like the more wolves, like the less food there would be.
Yes, that's a good point. If you have twice as many viruses inside of a person's body, it's not necessarily the case that there's fewer resources left. Yes?
Do the viruses need something else to reproduce? Do they inject?
Yeah, but these are all. What is the assumption here? What is the biggest difference? You know, like viruses are not like wolves. They're not preying on humans. It's contagious. Where are most of the viruses? Are they sitting around waiting to jump on somebody? They're already in your body, that's right. So the biggest difference between viruses and normal predators is that they're already in people's bodies. That's where they live, right? So let's start with a Lotka-Volterra style model of viruses, and then let's think about why it might work or it might not work, okay? So modeling epidemics. Okay, so first model Lotka-Volterra style. So let's have a host population. And let's say Y is the virus population. That's what we would do in a Lotka-Volterra style model. We have a population of rabbits or humans, and we have a population of viruses. Okay, and we want to see the dynamics over time. Now, let's make it very similar to the Lotka-Volterra model. In the absence of viruses, what is the equation for the hosts? Just think of the simplest possible model. Simpler would be exponential, that's right. So something like alpha x, right? Don't write this down yet. Okay? So in the absence of virus, this is what you would get. When you have viruses, then what do you think should happen? The population is now more sick, right? Okay? So what goes down? This alpha number goes down. Instead of making alpha dependent on y, we can reduce alpha by some function of y. So g of y, g of 0 is 0, right? So when there's 0 virus, you're back to alpha times x. But as the number of viruses increases, then this intrinsic growth rate goes down. Make sense? Okay, great. What about the virus population? Remember how we modeled wolves last time? In the absence of rabbits, what happens with the viruses? They die, right? And again, because we don't want to deal with things like aging and whatnot, let's just introduce a term of death. Okay, so in the absence of rabbits, you just die at an exponential rate. What about how can viruses grow? How can viruses be produced? By meeting hosts, right? So the more hosts there are, the more the viruses reproduce. And also the more viruses there already are, the easier it is for them to reproduce, right? So then you have something like constant times x times y. This looks just like the term in the Lotka-Volterra model. In fact, the only thing that's different in this model from Lotka-Volterra is that g of y in the Lotka-Volterra model, I think, is a constant times y, right? So it would be constant times x minus constant times x times y. Okay? We're making it slightly more general. Now, let's think about this model. What do you think would be wrong about this model? Why is this not appropriate? Or is it okay? For example, if you give me a population, how do you calculate the virus population? If you give me a number of people, like say there's like a flu going around campus, right? And we got you guys. How do we figure out the virus population? It's kind of hard, right? How do you know how many viruses are inside of somebody's body? That's not easy, right? And even if you knew that, would it really matter to know exactly how many viruses there are? What if somebody has twice as many, Krista, I hope you don't have the flu, but if you had the flu and you had twice as many viruses as Michael, would she be twice as contagious?
Probably not.
Not necessarily, right? The only thing that may matter is that she has a cold, right? Once she has it, it doesn't really matter how much virus she has inside. The point is she has the virus. So it doesn't really matter, the total population of viruses doesn't really matter so much. In fact, if you have a given number of virus population, like say, I don't know, 1 million or 1,000 million, and you spread that same population over 100 people or over 10 people, it makes a big difference. Right? In one case, you have 100 people that are contagious. In the other case, you have only 10. But it's the same number of virus. So what this means is that really what matters is not the virus population per se. It's how many people it's inside. Right? Okay, awesome. So the drawbacks of this model are, for example, that it's difficult to measure virus populations. So you could not, it's very hard to add up the number of viruses inside of a whole community. Even if you did know it, some viruses or actually some hosts have much more or much higher virus density than others. Okay, and so what really matters is not virus population, but what? The number of infected people, exactly. That's really what tells you the state of the disease in the population. Okay, the number of infected individuals. Okay, so slowly we reached the conclusion that viruses are not wolves. And a little more than that, right? So it's really not the way to go, okay? So based on these observations, some people back in the 1920s, again, in this case it's this is called the SIR model by two guys called Kermack and McKendrick. From 1927. Okay, so here's the deal. S is the population of susceptible individuals. What do you think is I? Infected, yes? And what about R? Good. Have you guys seen this model before?
Last quarter we worked on it really briefly.
Oh, you did?
Yeah, it was like the very tail end of the quarter.
Oh, okay. How much time did you spend on it?
Like a day.
Oh, okay. And it was a continuous model or was it discrete? Discrete.
Yeah.
Okay, all right. Because this one is continuous. Okay, so there you go. So here's the idea. You got a bunch of susceptible people. Okay, these people may or may not turn infected at a rate, we're going to describe this rate as beta. And the infected individuals at some point become recovered. And this rate is, I'm not sure if it's V or we should think about it as a Greek letter, but let's just call it V. Okay? So one thing that is not present in this model is the actual rate at which you turn from S to I. There's just this parameter, but actually it's more complicated than that. Because the rate at which these people turn into infected has to do with both this concentration and the infected concentration, right? If there's no infected people, these guys are never going to turn infected, right? And if there's a ton of infected people, these guys are going to turn infected very quickly, right? So let's think about this rate. S prime is equal to, do you guys have any suggestions?
Parameter times S and I.
Times S and I? You mean times S times I?
Yes.
Yes, very good, Patrick. So that's exactly it. This is very much in the spirit of the wolves and the rabbits, right? The likelihood of this transition happening is proportional to the number of infected, and it's also proportional to the number of susceptibles. Okay, all right. So what about the rate of infection? Oh, by the way, this is there's something missing here. What is missing here? Minus sign. That's right. Okay, good. So now here we put the same thing with the plus, right? So because these guys are turning into infected, so we now write plus beta times S times I. Okay, and we now take into account the fact that these guys are turning into these, right? So the rate at which infected turn recovered depends on what concentration. Does it depend on how many people are recovered already? No, right? It doesn't matter. Does it depend on how many people are susceptible? No, it only depends on the number of infected, right? Krista, do you want to try?
VI minus VI.
Good. Minus VI. Okay, so we write a beta in here, but really what we should write is beta times S times I, and this rate is V times I. And then I'm actually more comfortable with this graph, even though people usually don't write them, because these are the actual rates. This is the rate at which this is turning into that, and this is the rate at which this is turning into that. Okay, and okay.
Wait, why is it negative again?
Okay, this negative is negative because we're talking about the rate of susceptibles turning infected. So, you know, when this happens, this population decreases. That's why there's a minus. Now, this guy is gaining what this guy is losing. Whenever there's an infection, this guy goes up. So that's why there's a plus. But the recovery diminishes the number of infected. So it's a minus. There's a minus in here. And do you want to try the equation for R? No, it's not negative. The rate of recoverers is actually positive. Okay, they're just, you know, every time there's more recover people because there's no way for them to go down, at least not in this model. Natalie?
Is it VI
Plus or minus?
in front of it? The
Yes.
positive.
Positive, yes. Yes. Once again, this loss is this gain. Okay? Good. This is it. That's the model. All right? Now, there's a few things I'd like to point out. If you add all of these three together, what do you get?
0.
0. What does that mean? Okay, good. Does that make sense? That the population doesn't make sense? Population doesn't change? So S plus I plus R prime. So if you add everything up and you take the derivative over time, you get S prime plus I prime plus R prime, and that is equal to the sum of these things, minus beta Si plus beta Si minus Vi plus Vi, and that is 0. Okay? Now, question, does that make sense in this model? I mean, the populations are not constant in principle, right? Populations grow or decrease. So how can we get away with assuming that a population overall is constant? Isn't that like a really big flaw of the model?
Would we be assuming for death rate or constant?
Equal to each other, yes. Now, does that make sense? Is that really weird? What would be another way to justify that the population is not changing?
We only look at it over a short period of time.
Yes, Michael's got it. We're only looking at this over relatively short periods of time. And epidemics might take maybe a month, 2 months, you know, a season, right? You know, basically, it's like a flu season. Whereas the population grows much slower than that. You know, it might grow over years. If you look at only over population growth over a month, is maybe only like 0.5% or something like that. So it's so little that we don't need to worry about it. If we were looking at population evolving over years, then sure, we have to take into account population growth. Yes?
Aren't we also assuming that our disease doesn't kill anybody?
Okay, that's another great question. What would change in this model if the population, if you die from the disease as opposed to recovering from it?
There'd be a curve in a line.
It just is absorbed by the recovery.
It's absorbed by the recovery. I like that. What does that mean?
Well, I mean, if you assume that V includes deaths, then, like, once you're recovered, you can't get the virus again. And if you're dead, you also can't get the virus again.
Right. In this model, R isn't doing anything. So these guys might as well be dead. I mean, seriously. If you assume that these guys are dead, then the model is the same. Right? So we're just being like nice. We're just saying, being PG-13 here. This is, you know, you just get a mild disease and you recover and that's it, right? But if you died, then, you know, it's the same thing. Okay? But actually, it will make a difference for our next model. We're going to make a slight tweak, and then it will matter that these guys are actually alive, you know? So back to this constant population, this is okay, as Michael said, assuming assuming that epidemics takes place in a short time span. And you might think this is all theoretical and not very relevant to real problems, but actually this model and this problem of modeling epidemics is incredibly relevant. You guys might have heard of SARS or the flu, bird flu and things like that. And every once in a while there's a weird disease coming up in the middle of nowhere, like in Singapore. Well, Singapore is not the middle of nowhere, but it's some faraway place. And then you have to wonder, is this disease going to turn into an epidemic? Okay, does it happen every time that somebody gets sick from some new bug? Does it always turn into an epidemic? No, right? If you're able to contain it, or if it's not infectious enough, it never actually turns into an epidemic. The virus dies out, the people recover or die or whatever, and that's it. So the big question for epidemics is this budding disease going to turn into an epidemic in the whole society, or is it going to die out, right? And the question has very big policy implications. You're supposed to, if you think that this is going to turn into a big epidemic, you really have to do something about it as quickly as possible to try to isolate people and whatnot. So knowing this likelihood of something turning into an epidemic or not is a very important question. Okay, so let's go back to the SIR model before we analyze it and do a slight variation. And I'm going to call this SIRS. Okay? So what do you think is happening now? The recovered are doing what? They're going back to susceptible, that's right. So when would that be reasonable? When does that make sense? Well, first of all, they're not dying, right? They're actually alive. So we're back to this recovered model instead of dead. And second, well, some diseases, you can actually get the same thing over again, right? Like what? Like what? Okay, flu is interesting because flu you can get year after year, but it's actually a different disease. It's not the same flu. So for the one season we're looking at, say that we're looking at just one month or 2 months or something like that, once you get the flu, that's it. You're not going to get the same flu again. But some other diseases you might. Okay? Actually, I'm not sure exactly which one because the immune system is pretty good at preventing the same thing happening again. But maybe, I don't know, maybe the virus is evolving or something, and then after a while it's not the same virus, whatever, right? So basically, you can make the assumption that the same disease you can get more than once. All right. So what is different then? You have your S. You have this rate of transition between S and I. You have VI. And then what? You have this rate here of recovers turning susceptibles again. And this rate will have another parameter, let's call it beta, gamma. And this is gamma times R. Okay. Now, does anybody want to try and change the original model to include that? Who wants to volunteer? Minus beta SI. I prime is equal to beta SI minus VI. Okay, that's the original model. Now, what about the new model? Any volunteers? Yes, Daniel.
First equation, you add gamma R.
Oh, okay. Plus gamma R. And?
Oh,
What else?
So you have to subtract gamma r to r prime.
That's right. Good. You got the drill. That's it. Okay. Now, what Kermack and McKendrick did already almost 100 years ago is they did a analytical work. In other words, they actually tried to solve these equations and come up with an actual formula. And as you might expect, the formula was incredibly messy. It was like a big, complicated formula, lots of secants and whatnot. And then they said, okay, so the qualitative behavior is this and that. What we're going to do in this class is we're not going to bother with the exact solution. We're only going to look at the qualitative behavior, okay? Which will actually tell us pretty much just as much as what you couldn't get from the formula, okay? Especially, once again, I'm saying this again, even though I've said it before, is that because you don't know parameters and the real world is messy, you cannot expect that this formula is actually going to tell you the actual solution over time. You know, the formula will tell you this is, at every given time, this is exactly where you're going to be. That's actually too much of a prediction to expect to be true. It's better to expect something smaller. Let's just talk about the general behavior and see and compare that with the real world. Okay, so there's one thing that I would like you guys to get from this type of model, and that is something called the reproductive number. Have you guys heard about this before? Okay, all right. So what we're going to do is we're going to analyze this model, even though that model can also be analyzed. But let's just stick to this SIRS for a moment. And let's start thinking about steady states and whatnot. Let's do an analysis of this system. So steady states. Who can tell me like the obvious steady state? Zero, zero, zero. Okay, there's no population. Okay. What about a slightly less obvious one? Okay. By the way, we said that this thing is constant, right? So let's say that S plus I plus R is equal to N. Okay, this is the total number of individuals. So, but that means that 0, 0, 0 is not a steady state anymore. Okay, so Natalie, how would you change that? So that the sum of all of them is N and not 0. Sorry?
2 or 0, 1 of them is 0.
Which one is 0? Brian?
S.
There's no viruses.
Oh, yeah.
There's no what, Chris?
No viruses, so infected is 0.
Okay.
And recovered would also be 0.
Okay. Let's look at the situation. And so this is N, right? Let's look at the situation. Do you think intuitively should this be a steady state? Why is that?
Well,
Assuming no viruses.
if there's no virus that exists, then it would be.
It's like the giraffes,
Yeah.
right? Your favorite animal, Krista. If there's no giraffes, you're not going to see giraffes coming out
Yeah.
of nowhere, right? So if there's no virus to begin with, you're never going to see anybody getting sick, right? That model better be like that. If it doesn't have that property, we have the wrong model, right? So let's look at this. So if I is equal to 0, this term is 0. Because R is equal to 0, this term is 0. Okay? Because I is equal to 0, this term is 0. And I is equal to 0, this term is 0. R 0, 0. So, okay, fine. It's a steady state. Yes?
Technically, if there's no infection, then wouldn't the people not be considered susceptible?
Fair enough. You could still call them susceptible, even though, they might, if some bug came in from another country or something, then you might, right? But yeah, you're right. You're right. Then, yeah. Okay, now let's think about a non-zero steady state. Okay, so specifically, suppose that I is different from 0. let's say that I is different from 0. So if I is different from 0, what can we say about R?
R is non-zero.
R is non-zero at steady state. Why? Because I is non-zero.
R is being carried over
If R was equal to 0, okay, then it would not be a steady state. Okay. R is different from 0, and in fact, R is equal to, well, let's just write this down. So 0 is equal to VI minus gamma R. So that means that R is equal to VI over gamma. Okay, and it's different from 0 too, right? Okay, now what about S? Okay, S is at steady state. Oh, actually, no, actually, let's look at this guy over here. 0 is equal to beta S minus V times I, right, from this equation. So what can we conclude? So either this is 0 or this is 0, right? But I is non-zero, so beta S minus V is equal to 0, and that means that S is equal to V over beta. Okay, now we solve for how do we find I? We have a formula for S. We have a formula for R in terms of I. Okay. So now how do we solve for I? Yeah, we can do that. We haven't used that equation yet, but let's do the following. We know that S, I, and R are equal to N, right? So then we can plug in the formula for S and the formula for R, VI over gamma. And now we can solve for I, right? Yeah, okay. So this is N minus V over B, beta, divided by 1 plus V over gamma. Okay, that's it. Okay, so that's a steady state. Okay, now remember that for every one of these systems, we've said, you know, there's some parameters that make sense and some parameters don't make sense, right? So what do we want to have in this model? What condition do we want on the parameters? Or what condition do we want on the steady state? Could it be that the steady state is negative? That the number of inspectors at steady state is negative? No, right? So if we want this second steady state to actually be a real steady state, we want that that I, S, and R is bigger or equal than 0 at steady state, or actually bigger than 0 at steady state. For this second steady state. Okay. In particular, we want that n minus v over b divided by I plus v over gamma is bigger than 0. What's that? Oh, sorry, 1. Okay? Now, what happens if this is not satisfied? That means that that second steady state, the non-zero steady state, is not really a steady state, right? It's not biologically reasonable. Does that mean that that model doesn't make any sense at all in that case? What that means in that case is that we really only have one steady state, the trivial one, because the other one we throw out. The other one is not going to happen biologically because it's not going to give us positive solutions, values, right? So if this condition is not satisfied, the model is still a reasonable model, but it only has one steady state. Does that make sense? Okay. Now, what does this mean? Okay, so this thing is never going to be 0. We can just get rid of it. So this is the same thing as saying n minus v over beta bigger than 0. And this is the same thing as saying that n is bigger than v over beta. And this is the same thing as saying that n beta over v is bigger than 1. Okay? If n beta over v is less than 1, then the only steady state is n0, 0. Great. So there's something about this particular combination of parameters. Okay? There's something about it. I just want to throw it out in the air. There's something about that combination of parameters being bigger than 1. Let me look at a different type of analysis and show you that the same thing will happen. Another analysis. Okay, suppose suppose that S is roughly n. Let's say we have 1,000 people in this town or in this population, and we introduce a small number, like say only 10, or 3 of them become infected. So now still S is basically equal to n, okay? A small number of individuals become infected. Question: is this infection going to turn into an epidemic? Okay? So let's look at this model, and I want you guys to think about how we can tell that. You know, if you have S is very, very similar to n, let's say n minus, I don't know, minus a very small number, and we start with a very, very tiny number of infecteds. The question is that infection going to turn into a full-blown epidemics, or they're just going to die off?
Depends on how contagious the virus is.
Okay, it does. looking at the model, right? Well, how would you expect that to play? There's two different ways in which this can play. You can start, let's say that this graph is the graph of I over t, the graph of the infecteds over time. There's two different ways this can play. You can have a growing number of infecteds, then eventually goes down because they recover. This would be an actual epidemics. Or you could have that number just dwindling down to zero without actually causing an epidemics, right? These are the two different things we want to differentiate. Is it going to grow and then eventually go down? Or is it going to dwindle down without causing any trouble? So how can you tell?
Recovery rate.
No, it's actually very simple. Look at that first moment in time and ask yourself the question, is the population of infecteds going up or down? Right? It's easy, right? So remember that the infected population has the equation beta Si minus Vi. And we want this thing to be positive. Right? That is the question. Is this thing going to be positive? Now that thing is the same thing as asking, is beta Si going to be bigger than Vi? Right? But actually we can cancel out the I because remember I is a small number but it's positive. So the question is beta S bigger than V? And now what? Remember what the value of S is? It's almost N. So this is basically the same thing as saying beta N is bigger than V. And this is basically the same thing as saying that beta N over V is bigger than 1. In other words, if this combination of parameters is bigger than 1, we expect a small number of infecteds to turn into a larger number of infecteds and the epidemics to grow, to appear. If this is less than 1, then we expect the number of infecteds to just dwindle down to 0 and it never turns into an epidemics. Make sense? Look at that. It's the same. Right? So we have two different ways to justify that this combination of numbers is actually very important. If this combination of numbers is bigger than 1, you have an epidemics. If this is less than 1, you don't have an epidemics. Yes, Mike?
So beta is like how infectious our disease is, right?
Yes.
So then we're saying for a more infectious disease, we require a smaller population to cause an epidemic. But for a less infectious
No, because as long as it's bigger than 1, you're okay. So it doesn't matter what the population is. If it's infectious enough, then you're okay. The infectious is going to turn into an epidemics. So we're not asking for this to be equal to 1, if that's maybe what you meant. If beta is really large, you need n to be smaller for this to be equal to 1. But that's not what we're saying. We're saying is if this combination of parameters is bigger than 1, a small number of infected is going to blow into a larger epidemics before it dies out.
So we have some kind of threshold then at beta n over v equals 1.
Yes. Yes. And you did raise a good point. If beta is very, very large, then n can be smaller and still turn into an epidemics.
Right.
Okay? So here are different ways in which we can turn into an epidemics. Very infectious disease, huge population, or very slow recovery. All of these make sense, right? If you have the right combination of them, you're going to have an epidemics. Now let's look at the units of these things. So what is the units? What is the unit for V? This is the population is going to be in numbers, okay? Number per time. Okay, so this is number per time. This is going to be only one over time. What about beta?
One over
1
time, remember?
over time times number. And what about n? It's just number, right? So that means that beta times n over v is in units of 1 over time per number times number. Okay, and this is unitless. So even better. Okay? Now, you can actually think of this number, we're going to give it the name R naught, or the reproductive number. So V. You can think about this as the number of people infected on average by a given infectious individual. So let me describe this a little better. So suppose that Krista got the flu, and I'm sorry to pick on you, Krista. I hope you don't get the flu, but
Me too.
so the reproductive number is going to be the average number of people that Krista is going to how do you say, infect over the course of the disease. So from now until Krista gets better, how many people is she going to infect? So think about it. If on average she's going to infect 3 people, right? Then if you start with only like 5, a small number of infected people, like say only 5, then before these guys are done, there's going to be 15 people with the disease. And before those guys are done, there's going to be 45, and so on and so forth, right? So this small number of infected is going to turn into a large epidemics before it dies down. Okay? On the contrary, suppose that on average, Krista is only going to infect half a person. Now, the chance that she's going to infect half a person is very low, but she might infect either 0 persons or 1 person. So R0 means on average, she's going to infect only 1/2. Okay? So that means that if you start with, let's say, 4 infected individuals from Singapore that had some kind of weird flu, if they on average only infect half, that means that after a while there's only going to be 2 left, or 2 new individuals, and then out of those 2 maybe just 1 is going to get infected, and then 0. Okay? Now you have to realize this is all a stochastic phenomenon. Krista might actually infect more than 1 or 2 or 3. We're just talking about averages. Okay? And this only works when the noise effects are assumed negligible. Okay? But it's still a useful information to have. So there you go. This R naught is basically the most significant parameter to compute from this model. And so people from the CDC are going around like crazy trying to figure out when there's a new disease. What is the reproductive number? How many people is each patient going to infect? Okay? Oh, you don't have time. Oh, okay. Okay, so let me just write one more thing, and then we're done. It's the phase diagram. Of SIRS Okay, so the first thing you do is you write R is equal to N minus S minus I. Okay? Because you can always write R in terms of the other variables. You can essentially replace it away. You can get rid of it completely in the equations, so you end up with a 2-dimensional system. Okay? That's a trick. And so because we now have a two-dimensional system, we can do things like the Nullcline analysis and all that stuff. And you can show that there's one steady state which is actually stable. Okay? And it looks like this. So if you start with even a small number of infecteds, you're going to go up to a large number of infecteds before you kind of settle down. And you settle down to this situation where there's kind of an endemic population of infected people, which, by the way, is the steady state that we found. Okay? There's also the steady state where this is n and I is 0. This is also a steady state. Okay? Now, this is in the case that the reproductive number R0 is bigger than 1. In the case that R0 is less than 1, and remember R0 is that combination of parameters, you have the same steady state, but now the dynamics is stable towards that point. Okay? And that's significant because if you started with a small number of infecteds, okay, then you're going to go down and converge towards that point without causing an epidemics. So this going up here, this event of going up, that is the epidemics itself. Okay? You see, you start with a small number and the number goes up before it goes down again. In the case of the R0 less than 1, you never actually have an epidemics. It dies off. And you can draw similar phase diagrams for the SIR model. In the SIR model, you don't have this endemic population. You really only have that one steady state. And the only question is, are you going to go up and then down, or are you going to stay down and never cause an epidemics? All right, that's it. Do you guys have any questions?